Functions are a big deal in calculus, so we need to do a pretty good review on that. Okay, so let's take a look at kind of what we mean by an inverse and look at that a little bit. So what I'm going to do on this one is we're going to graph the inverse of this function, and I'll show you what that is and see what you remember on that. So basically what I'm going to do, this one's a pretty easy one to do because it's a line, and oh God, more issues. Everything works when I test it in my office before class, and then the minute I get to class, nothing works. Let me try again.
It's probably Skynet.
What's that?
It's probably Skynet.
Yeah. Oh, come on. Just got to write on it. Oh, you know what? The teacher did not plug this in. That's what the problem is, okay? Always make sure everything's plugged in. There we go. Hey, finally. All right, now I'm ready to start. Okay, so anyway, what we have on the line here is we need to just find, like, two good points, okay, on the line, okay? 1 point, of course, is 0, 0. So let's label a couple of points on there. There's 0, 0. You guys probably got better eyes than I do, but I think 1, 2, 3. I'm thinking that's a point 1, 3. What do you think? Am I right? Am I seeing that okay?
Yeah.
Okay. And then another thing I'm thinking is probably -1, -3. Does that look okay? All right. So what we want to do on this, I'm just going to have you make a table of values. Really all we need is a couple of points on a line anyway. So we have x and then we have y. So we have like -1, -3, 1, 3, and then we have 0, 0. Okay. Now what we're going to do is we're going to make another table of values, but this time we're going to do f inverse. And I'll ask you, what do you remember? How do you make an inverse? It's very easy. Yeah, you flip the points around, okay? It just means x becomes y, y becomes x. So what we're going to do is just flip these things around. So we have -3, -1 now, 3, 1, and of course 0, 0 is still 0, 0, okay? So what we're going to do on this then is I'm just going to pick another color, and we're going to plot these 3 points, and then we'll have an inverse, okay? So if we start with this, we'd have like -3, -1 would be a point, 0, 0 is a point, then you would have 3, 1 would be a point like that, and then you've got your basic line like that. So what I drew there is this thing is the graph of f inverse of x, like that, okay? So that's what inverses are. It just means you flip the x and y coordinates to make out. Does that make sense? It's nothing to it. Okay, I'm going to ask one other question and see what you guys remember on this. Do you guys remember how these two functions are symmetrical? They're always symmetrical in a certain way at their inverse. Anybody remember what that is? Y equals what?
Y equals x.
Y equals x, good, exactly. So if you drew the line y equals x, then that's the symmetry on that. So let me just explain what I mean by that, because inverses are always symmetrical, kind of like at a 45-degree angle. So if you have y equals x, if you do a table of values for y equals x, it's real simple. You'd have like -1, -1, 0, 0, 1, 1, and so forth. It just means x and y are the same. So one thing that you also want to put on your notes is just kind of sketch out that line, y equals x, and that's just going at a 45-degree angle. You don't have to be perfectly accurate, but just to remind you, that's how things are symmetrical, okay? That's what inverses are. There's nothing to it. We deal with that quite a bit in calculus, so it's something you're going to see. Inverse functions is something we're going to definitely look at, okay? Any question on that? Okay, let's do the next one here. And again, let's just kind of take the same approach. Let's look at the graph that I gave you. And let's find maybe like 3 or 4 good points, okay? Just got to find good points is the thing. So this looks like I'm going to go with negative 4, 0. Okay, that looks like a good point. This point's probably going to be negative 3, 1. Okay, that point right there is going to be, it looks like 0, 2. I like that point. Now I need to find one more. I think, let's go way out here and, let's see, that one's, I like this one right here. That looks like 5, maybe 5, 1. So I'm going to go with 0, 2, and I'm going to go with 5, 1. Okay, those points look okay to everybody? I'm getting some funny looks from you guys, so.
I think it's 5.
5, 3, is that what it is? Yes, I like that better. I definitely like that better than 1. Okay, all right, so we have that. Now, what we're going to do is we're going to just go ahead and make a chart for the inverse. This basically is x and f of x is what that is. Now we're going to do f inverse of x. So what do we do with the points? Turn them backwards, right? So we just go 0, negative 4, 1, negative 3, 2, 0, and then 3, 5 should be a better point on that, and then we're just going to plot those then, okay? And you'll see that it still has the same symmetry. So you can go ahead and plot these points. There's 0, negative 4, there's 1, negative 3, there's 2, 0, there's 3, 5, and then it's going to go up kind of like that, okay? That's your inverse. Now, do you guys see the same symmetry on that? Y equals x. So the idea would be on this, if you just sort of sketch like that 45-degree line on that, then it'll have that particular type of symmetry like that. So it's just kind of going something kind of like that. That's my y equals x line like that. Okay? All right, how's that look? Okay? Yeah, you probably in college algebra didn't do much with inverses. It was more of a skill to get you at least started on, because you definitely need it for calculus. We actually do quite a bit with inverses in calculus. Okay, any questions so far about anything? Okay, all right, let's do one more. This one's kind of different. It's the same exact idea, but let's just do one more of these, and then I want to go through how you actually find the function that's the inverse. So let's find some good points on this one then, okay, just enough to get the idea. So let's see, you can help me out a little bit if you see anything that looks like a good point.
So 3, 1.
What do you think? Yeah, 3, 1, that looks like a good point. Okay, so let's use 3, 1. What do you think? Negative 3, negative 1, that looks like a good point. Okay, and let's see, let's go just kind of estimate something in here for the idea. Let's say maybe you have like, I'm going to do something like this. So like 0.5, just to show you something. At half, it looks like maybe that's 8. That's just my thing, okay? I'm estimating, okay? And if I went to like negative 0.5, you know, which would be like halfway to the left, maybe that's down 8. Again, that's just estimating, okay? You see what I'm doing? Okay? Now, what I'm going to do on this one is, if you look at this, this one's kind of an interesting graph, because now if you turn those backwards and you make a table of values for the inverse, well, again, you're just going to flip everything. So you would have like 1, 3, negative 1, negative 3, 8.5, and negative 8, negative 0.5. Now, if we plot those points, and I'm not going to do this on there, I'm just going to up here and point this out to you. What happens on this, if you plot 1, 3, look at this, over 1, up 3. You're already on the graph, aren't you? Okay? If you go over to negative 1, negative 3, that's left 1, down 3, so you're already there. Okay? And if you do 8.5, way over 8, that looks like it's on the graph. So what do you think's happening on this problem?
It's just
Same graph. Okay, it's exactly the same graph. So it turns out this is what we call a rational function. Sometimes a function is its own inverse. Okay, it's just the way it is. Now here's how I knew that. If you drew that y equals x line, wouldn't it already be symmetrical?
Yeah.
Okay, so it's already symmetrical about that line. So therefore it's just its own inverse is the idea. So this one would just, you can write a note on this if you want to, it's just sort of its own inverse. Inverse is the same. Okay, and again, if you did that y equals x line, just think of that as going at a 45-degree angle. And you can see it's symmetrical about that. If you fold the graph over that line, then they're going to match up. Okay? All right, how's that look to everybody so far? Okay? All right. Yes?
Is this going to be true of all odd functions, or do you have some?
Okay, well, I think what you're conjecturing is, yeah, this is an odd function because it's symmetrical about the origin. Right. Yes, that's right. So if you do have some sort of an odd function, now you've got to be a little bit cautious about that, but it will generally, since odd functions are symmetrical about the origin, they are going to flip over that line y equals x. Okay, so generally, if you have to watch out about the domain on that. One thing that you probably learned a little bit of in college algebra is you can only do an inverse of a one-to-one function. You may remember something about that. Yeah. So if it's a one-to-one function, yes. Okay?
All odd one-to-ones.
Yeah. Okay, so let's see. Let me move to the next thing here. Okay, now the next thing I want to do is just kind of show you, this should be review for you too, hopefully, is without graphing just how we find an inverse. Okay? And the idea on this is what you do. You basically just replace the variables. X and y trade places, you solve for y, and then you got your inverse. Okay? So what we're going to do is just a couple of simple ones here, this number 4 and 5, and actually find the inverses. I'm not going to do any graphing on this. So what you would do with number 4 is you would start off by just doing that, okay? Y equals 8x minus 3, okay? All right, now, without getting too technical on this yet, you have to have what's called a one-to-one function. So let me see if you guys remember anything about one-to-one functions. If you went through and graphed this line, that's a line, what would be the y-intercept of that line? Negative 3. What would be the slope? 8 over 1. How do you do a slope of 8 over 1? You go up 8 over 1, right? Now, I'm just going to kind of wing this, okay? You go up 8 over 1, so you'd have a line that looks something like that. Does anybody remember what test you apply to tell if something's a one-to-one function? There's two tests you learned. You learned the vertical line test. That tests if something is a function. Horizontal line test tests if it's one-to-one. What one-to-one basically means is every y matches with exactly one x. It always does, okay? So this one is a one-to-one function, okay? Horizontal lines always go through one point. And that's the only kind of thing you can do an inverse on, because what would happen if it wasn't one-to-one, then your inverse wouldn't be a function anymore, okay? So the idea with this is you got to make sure your function's one-to-one. If it isn't, you have to redefine it so it is. But I'm not going to worry too much about that technicality now. We'll end up looking at that later in the semester, though. So here's what you do. You go ahead and just switch the variables. That's it. Okay, if you took trig like last semester, you did a little bit of work with inverses also. Now what you do is you solve for y. You can do a lot of this in your head. You're just moving the 3 to the other side, adding 3 to both sides, so you have x plus 3 equals 8y. At this level of a class, just learn to rearrange if you're not already doing that, okay? You don't have to show that you're adding 3 to both sides. Just in your head do that, okay? Now what you do is you divide by 8, okay? So you would write, instead of writing y, you write that as f inverse of x, and then you can write it this way. That's fine if you write it that way. You could also write it as 1/8 x plus 3. To me, it's just important that you understand that they're both the same thing. That's just two ways of writing the same expression, okay? All right, how's that look to everybody? Okay? All right, you guys go ahead and do number 5. See if you can do the same thing I did, okay? That is a one-to-one function. I'll explain why that is in just a minute here, but just go ahead and do 5 yourself, give you a couple minutes to do that. This is not a hard one to do. It's got think about what the opposite of cubing is. You know, your answer should have the operation that's the opposite of cubing. All right, you know what that is? Not square rooting, but cube rooting, right. Okay, you're thinking right, good. Okay. Should have a cube root in there. Okay, no, that's what I've done so far. Okay, and you always start by just switching the variables. Sometimes students forget the last move. What's the last move? You do cube root. That's how you undo cubing, is you cube root. You undo squaring by square rooting. So now what you do is just do cube root of both sides, and be sure you do the cube root of the whole thing. So one answer would just be, the best way to write this is just cube root of x plus 1 over 5 equals y, and then you can write the y just as f inverse of x like that. Okay, so that's the idea. Okay, how do we feel about that? Okay, all right, it's not too bad. Okay, logarithms, oh my goodness. Okay, that in calculus, now we're going to do a very rough review of logarithms, and we will review that quite a bit as it pops up in the class, but this is one of the areas that is typically weak for a lot of students in calculus. Part of the reason is, if you took college algebra, that's been a couple of semesters, and Trig, you don't even touch logarithms, okay? So it's easy to forget a little bit about them. But logarithms are, the idea is they're a certain kind of an inverse function. So what I want to do is just review a few basic things that it's helpful if you review them a little bit now, because a little bit later in the semester we'll deal quite a bit with logarithmic functions. So the idea on this graph here is, and I'm going to have you guys make a table of values on this, because I think it's important that you kind of learn it this way. 2 to the x is an exponential function. Anytime you have a number to a power, where your variable's in the power, we call that an exponential function, okay? So I'm going to just have you put a couple of numbers on here, just enough to get the idea. Let's do -2, -1, 0, 1, and 2 like that, okay? Now let's work this out. There's things with negative exponents that are also beneficial to review with students also. All right, what we're going to do is just plug in and work out. What's anything to the 0 power? That's 1, okay? What's anything to the first power? Itself, okay, so that's 2. And then 2 to the second, of course, that's 2 times 2, so that's 4, okay? Now, if you go to 2 to the -1, what's 2 to the -1? It's 1 over 2 to the first. Remember, if you have a negative exponent, you have to rewrite it as a positive exponent. So that's really 1 over 2 to the first. Okay, oops, I don't know what in the world I did there. So what that is that's 1 over 2 to the first. So we're just going to write that as a half. Okay. Then if you get into 2 to the -2, that's 1 over 2 to the second. So that's a fourth. So when you're doing a negative exponent, you're not getting negative answers. You're getting fraction answers. And it has a nice pattern. I mean, you can predict what it's going to be. If you had 3, you would have 9. If you had -3, you'd have 1/9, right? That's the symmetry behind that then. Okay. Now what I'm going to do, for the logarithms, I'm going to have you make another table of values. So we have x, and then we have y equals log base 2 of x. Okay, now you don't want to just pick any number. I already know that they're inverses. That's one of the things you learn in college algebra pre-calc. So what I'm going to do is I'm going to switch these things around. I'm going to use these same y values that we have here, but I'm going to change them into x. And then I'll just sort of prove to you that you would get the backwards answer anyway, okay? All right, now this is what I want to see if students remember, because a lot of times students don't. Let's start here because it's easier to see. Let's do log base 2 of 4. Okay, then let's do log base 2 of 2, log base 2 of 1, and so forth like that, okay? And let's see if we remember this, because see, all a logarithm is a logarithm is an exponent. If you see an expression like this is what you're thinking. What do you raise 2 to get 4? 2. How about this one? What do you raise 2 to get 2? 1. What do you raise 2 to get 1? 0. See how it's given those numbers? So it's backwards. The logarithm's backwards of an exponent. 2 to the second is 4, so 2 goes there. 2 to the first is 2, 1 goes there, and so forth. Okay? So that's how that works out. So logarithms and exponentials are inverse operations of each other. So if you just work the details out on that, you're going to get 2, 1, 0. Even when you get to this point, log base 2 of a half, okay, that's actually equal to -1. And the reason is because if you do 2 to the -1, like if you look at this expression, don't you just get a half? Okay, so that's what you get. Okay, so those are inverses of each other. That's kind of one of the key things that you want to remember about a logarithm is it's opposite of an exponent. Okay, just like square rooting is opposite of squaring, logarithms are opposite of exponents. Okay, that's the idea. They're inverse operations. Okay, all right. So the other thing that you never want to forget about logarithms is how to change them back and forth to the two forms. So like this is a log form, log 2 16 equals 4. The exponential form is 2 to the 4th equals 16, and so forth. This one, 7 to the 0 equals 1, and so forth. Okay, you guys remember that? Okay, if you remember that part, that's a help. It's a big help. Okay, now we're going to do a few equations, and probably look maybe at the change of base formula too. I just tried to pick out a few areas. Okay, so when you're solving an equation that's got logarithms in it, you'll see this later applied to the context of calculus when we start working with derivatives. And the way to do this one is write this in exponential form. So tell me how you write number 7 in exponential form. 3 to the 4th equals x, right? Okay, this is an easy problem to solve because look at that, it's already solved. Okay, so you would end up, if you'd worked out 3 to the 4th, you would get 81. The answer to that problem is 81. Okay, well, it's always helpful anytime you're learning any type of an equation in math. The only way to really understand it is just to check it. Okay, so let's check it. If you go back to the beginning of the problem and replace x with 81, let's look at why that's right. Well, how do you know it's right? Well, what is 3 to the 4th? It's 81. Okay, so it's right. Okay, does that make sense? Okay, so that's how you check a logarithmic equation, is you replace x with its value, write it back in exponential form, and it's going to have to work out. Okay? All right, tell me on number 8, how do you write that in exponential form? 2 to the 5th equals x. Good, same idea. So that's 2 to the 5th equals x. When you work out 2 to the 5th, you'd get 32 if you multiplied that out. 2 out 5 times, you'd have that. Okay? So that answer would be 32. Okay, there's a key thing on this one that I want to ask you is, notice that there's no base there. How come? Because a log, and a log is what? Base 10, right? Okay, so it's understood to be base 10. Okay, that's just the idea. Now from here it's the same thing. What you would do is if you write this in exponential form, now I don't know why I put a negative 12 there. I do stuff like that a lot. So this is 10 to the negative 2 is equal to x like that. Okay, that's how you do that. And then what do you do with 10 to the negative 2? You say 1 over 10 to the second, and then you can work it out from there. See, so you have 1 over 10 to the second. 10 to the second is 100. So you get x equals 100 like that. Okay, that's just the rearranging of logarithms to exponential form. Okay, how's that look there, buddy?
I have a question.
Yeah, go ahead.
So I just found out that the 10 with the exponent, that's also called the antilog.
Yes.
Will we have to like basically use the antilog to undo certain things?
Yeah, in certain instances, see what happens if you have. I'm glad you said it. I never hear anybody use that terminology anymore. The anti-log is the same thing, though. If you were doing something like if you had, say you had log base 10 of, let's see, I was kind of trying to think of something like this. What you're kind of what you're doing on this, if you're doing an anti-log, is you're really trying, it's really the same thing as writing something in exponential form. You're trying to find the exponent for a certain expression. For instance, if you have something like, this is a good example, 2 to the x equals 16. Okay, you can write that as log base 2 of 16 equals x. Okay, so what you're doing, when you're talking about an anti-log, what you're doing is you're finding the exponent that satisfies that expression, which would be 4, right? 2 to the 4th is 16. Okay, so what we're really doing when we're writing that in that exponential form, log form is what you're talking about. That's a terminology I don't think hardly anybody uses anymore. Okay, let's do one additional one here. Now this one right here is an exponential equation. So I wanted to do something just a couple of different ways on this problem. But the way I'm going to do this problem is there's a relationship between 2 and 4. I've designed this problem so you can do it without knowing anything about logs. You were talking about anti-log. You could do a log of both sides of this equation. And then that's kind of what you're getting at there. Okay, what's the relationship between 2 and 4? 4 is 2 to the second. Okay, I put that 4 there with that idea in mind. So I'm going to write this as 2 to the 10 minus 2x. And I'm going to rewrite that as 2 to the second. Okay, now, this is real logical. At least I hope it's logical to you. Notice those bases. Those things I'm circling, that's the base. If those are the same, I mean, just think about this. If you had 2 to the 5th equals 2 to the box, what would have to go in the box? 5. Okay, the idea is if the bases are the same, so are the exponents. They have to be. It's the only thing that makes any sense. So what you do from this point is you reason out that those things I highlighted in yellow are the same, so that's your equation that you would solve. So you would have 10 minus 2x is equal to 2. Solve that equation, and you've got the answer to the equation. And I'll prove to you why that's right in just a minute. So now one of the things I'm going to do on this, you can subtract 10 from both sides. You can do at this level, you can do whatever you want to in your head on a basic equation. So that's negative 2x equals negative 8. Then you can divide both sides by negative 2. So you get x equals 4. Okay, like that. Okay, that's the answer to the problem. Now, so does that make sense what I did on that? Tell me, I don't know. Makes sense to me. Okay, if the bases are the same, the exponents have to be. Let's see if we're right. Okay, so what we're going to do is we're going to do 2 to the 10 minus 2 times 4. Work it out and see if we get 4. Okay, that's what we're checking in the problem. So what we have is 2 to the 10 minus 8 is what that is. Okay, so that's 2 to the second. Is that 4? It is, so we're right. Okay, so that is a procedure that you can use in certain cases, okay, on an exponential equation, all right? So that's how you could do this one. I think I put another problem at the side that I wanted to go ahead and do because this one you have to take a slightly different approach to, okay? But the approach I'm going to do on this second problem could also be done on the one I just did, okay? But what I wanted you to notice is 4 was a power of 2. Okay, if I would have put 16 there, it would have worked because what's 16? It's 2 to the 4th. Okay, that's the idea. Okay, so let's see if we remember anything about how we would do something like this. That's a little bit different idea. Now see, 3 is not a power of 2. So, anybody know what you do on a problem like this? You have to do something to both sides of the equation.
Oh, convert it?
Take a log. Take a log of both sides. Now, it's your call what you do on this. You could do a log, a base 10. It could be a ln. It doesn't matter. Okay, we're going to end up getting probably an irrational number on this anyway. So what I'm going to do on this is we're going to do an ln. In calculus, we're going to do ln almost always. We're not going to do anything other than ln that much. So remember, what is ln? It's log base e. Does everybody remember that? Okay. So what I'm going to do is I'm going to do the natural log of both sides. Although if you did a base 10 or any base, you would get the right answer. So I'm going to just do that like that. Okay? All right. Now this is the kind of background stuff that maybe you hadn't done in a while. Okay? There's a property of logs you usually learn in college algebra. Do you guys know what you can do to that exponent I circled? You can bring it down in front. Okay? That's a property of logs. So that thing can go down in front. So what you would get is 10 minus 2x is equal to ln 3 like that. Okay? That's why you do the log of both sides, because you take advantage of that property. Okay? Let's see, I think I missed my log here, so let me erase that. I made a stupid mistake there. Okay, so that comes down, that's still ln 2. That's equal to ln 3 like that. Now it's just a matter of getting the x by itself. Now you can do this in several different ways. What I'm going to do is just go ahead and divide both sides by ln 2, because that's a number. So I would have 10 minus 2x equals ln 3 over ln 2, like that. Okay. Then I'm just going to rearrange. Just move the 10 to the other side. And you could write this as ln3 over ln2. You're subtracting 10 from both sides, so you can do it that way. This is just one approach too. Okay. You could also move the x to the other side and the logs to the other side. Doesn't make any difference. Okay. Now what I'm going to do on this is, instead of dividing by -2, because if I divided by -2, I'd get kind of a real complex looking answer on that. So you want to have some flexibility. What I'm going to do is multiply both sides by -1/2. Just because the answer looks better. That's the only reason I'm doing that. Okay. And then that'll give that to me like that. And then what I would do with this is I would have x by itself now. And I would go ahead and maybe just distribute this out. So I would have like negative ln3 over 2 ln2. And then half of 10 is 5, but two negatives would be a positive. So probably the best way to write this exact answer would be 5 minus ln3 over 2 ln2. That's the answer to the problem. That's the exact answer of the problem too. Okay. Now there's more than one way to solve that equation after you do the logarithm of both sides, but that would give the exact answer of the problem. Okay. Does that look familiar? Okay. All right. Okay. We'll do that kind of stuff when we get to the point a little bit later in the calculus where we do that. The other thing I want to look at to finish this up is the change of base formula. So I want to look at that a little bit, because you actually use the change of base formula quite a bit in calculus. When we get to the point in the class where we use this, it'll help you kind of not have to memorize a basic derivative rule that we learned. So here's the idea. If on a calculator, what happens on a calculator is it will only do certain things. It'll do a base 10 log. It's going to have the log key, and it'll do a base e. So if for whatever reason you have to do something other than a base e or a base 10, then you're going to have to use your calculator and use the change of base formula. So the change of base formula basically just goes like this. If you're doing the log base 9, for instance, there's two ways you do this. One way you can do this is you can do the base 10 of the 5 and then divide it by the base 10 of 9 like that. Okay, and then you can get your calculator out and you can do that. Or you can do this. You can do ln of 5 over ln of 9. And it gives the same thing. So if you took your calculator now, and let me see if I can get this calculator so it's viewing the right way. So what you can do on this calculator, so if you do like the, you can just plug this in your calculator like this. So if you do like the log of 5, and then divide by the log of, what was the other number? I already forgot.
9.
It was what?
9.
9, okay. All right, so we get this. And see, that would be the value, and it's an irrational number. The decimals repeat, kind of like pi does. Now notice if you did ln of 5, and then divided that by ln of 9, then of course you get the same answer. So it doesn't really matter what you do, okay? You're going to use ln more than often than you are any other log in calculus, okay? All right, so that would be the idea, okay? Everybody remember something about that? Okay, that's a real simple thing to do. Usually do a little bit of that in college algebra. Okay, let's go to this last page on this, and then we'll do a couple other things. Then I do want to do a trig review also today before we kind of start our next chapter is where the calculus begins. Yes?
Yeah, on that problem we did before, the 2 to the 10 minus 2x equals 3, could we have done that one by just rearranging it and say log base 2 of 3 equals 10 minus 2x and solve from there?
Say that one more time.
So could we have rearranged this to say log base 2 of 3 equals 10 minus 2x
yes.
and solve from there?
Yes. Yeah, you're saying use a base 2 log. Is that what you're saying? Yeah, that's fine. Okay. The thing, and see what eventually you would get to the same answer. See, like on this is the exact answer. It was really a personal decision to do ln. You can really choose any log base that you want to. ultimately, if you wanted to get an approximate answer, this one is easy to do on the calculator because you have an ln key.
Right.
Yours, if you had an ln2, base 2 in your problem, you'd have to use change of base formula in order to get an approximate answer on the calculator.
Right.
Which is fine. Okay.
Yeah, I think actually the DI-84s will do any base anyway. So
right. So that's fine. I usually just use ln. That's kind of standard.
Yeah, I just figured it would skip a couple steps because you don't have one log in there.
Yes. Okay, so with this one, we're going to write this as base e. So if you write base e, you're going to use an ln, okay? So you're going to use the change of base formula. So if you have log base 6 of x, this is just a mathematical expression. That's the same as ln x over ln 6. That's all I'm wanting you to do on that problem. It's just that. Just learn how to change any log to an ln, or change any log to a base 10 log, okay? All right, so if you change it to base 10, what do you use? Log, L-O-G. So on this one, if you have log base 5 of x, that would be equal to log of x over log of 5. You always divide by the log of whatever the base is. That's change of base formula, okay? All right, so you'll see why this is useful in calculus when we start dealing with derivatives of logarithmic functions. And just the knowledge of change of base, it helps me keep me from having to memorize a formula in calculus that I never forget, that I never remember anyway. So I usually just teach you to use this formula. Okay, let's do this last one here together, and then we'll kind of start a trig review here. So what we're going to do is graph the function. I've already talked about this a little bit. So we're going to do x and y equals 2 to the x. So we did this problem a little while ago. I just already had the graph on there. So if you're graphing an exponential function, one thing you want to know about exponential functions that's kind of important, like if this number is like a number that's bigger than 1, like 2 to the x, 3 to the x, 4 to the x, then it's exponential growth. It starts low and then it gets out of control. The bigger that base is, the faster it gets, reaches infinity, I guess. Okay, and then if this number here is between 0 and 1, I'm talking about that number right there, if it's in the middle of 0 and 1, then it's going to be exponential decay, where it starts high and then it goes down like that. So exponential growth starts low and gets high, whereas exponential decay is opposite. It starts high and then levels off. This is an exponential growth curve, and the reason I know that is because that number 2 is bigger than 1, okay? So let's just use these values. This is like -2, -1, 0, 1, and 2 like that, okay? We already did this a few minutes ago, so it's the same thing. So we're going to do 2 to the 0, 2 to the 1, 2 to the second, 2 to the -1, 2 to the -2, and so forth like that, okay? Now we're just going to crunch it out, and we'll draw a graph, and then we'll graph the inverse, and then we'll talk about what the inverse is, okay? Okay, so let's see. With this one, that's 4, that's 2, that's 1. What was 2 to the -1 again?
Half.
A half. How about 2 to the -2?
Quarter.
A fourth, okay? You want to be sure you remember negative exponents and how they work. So if you go through and do your graph then, and just now go ahead and plot your points, you're going to have like the point 0, 1. You can have the point 1, 2, the point 2, 4, and then this thing just the curve kind of goes like that. Okay, then what it does is it levels off at the x-axis. Okay, now let me ask you a basic fundamental question. Will that graph ever touch the x-axis? No, but it will get close to it, right? It'll get infinitely close. If you used like x equals -1,000, then you would have 1 over 2 to the 1,000. Okay, which basically is a number just real close to 0, okay? So it never reaches that x-axis, okay? Now, let's do our inverse, okay? So the inverse, remember, if we do that, we're just going to do, flip the coordinates. So we're going to have a fourth and -2, a half and -1, 1, 0, 2, 1, 4, 2, like that, okay? Then that'll graph your inverse. So if you do that, you're going to have 1, 0, 2, 1, 4, 2, And even if you did these fractions, like if you did a half -1 would be there, a fourth -2 would be there. So your graph does this. Now let me ask this question, okay? Does the graph that I drew in green, does it ever touch the y-axis? No, okay, it just gets close to it. That's when you learned about those as being asymptotes. And again, this is what f of x is. This is what f inverse of x is. And then that thing was symmetrical about what line? Y equals x. Okay, like that. So that's kind of a summary on inverses. Now what I want to do to kind of close this off here is I want to go ahead and do the inverse, which is a logarithm. I hope that you know it's a logarithm, but I'm going to go ahead and just take you through the steps of doing this inverse just to prove to you that it's a logarithm. Okay, so let's do exactly what we did earlier in class on an inverse. Okay, all right, I want you to find the inverse of y equals 2 to the x. How do you start?
Take log of both sides.
Switch the variables. Okay, okay, and it is a one-to-one function, so you go ahead and just get x equals 2 to the y. Okay, now what do you have to do? Solve for y. Okay, now y, the only way to solve that for y is to use logarithm of both sides. Okay, so what I'm going to do on this is, you could take any log that you wanted to, but it's advantageous on this problem to do base 2 log because of that 2 there. And see, that's kind of what you were talking about, Stephen, on that problem you were doing a minute ago, I think. Something kind of like that, which is okay. So we have log base 2 of 2 to the y like that. Okay, all right, so we have that. All right, then what we'd have is this is log base 2 of x. So you can bring the y down like that. Okay, so that would be y times log base 2 of 2, like that. Okay, now can you tell me what log base 2 of 2 is?
1.
It's 1. Why? Because 2 to the first is 2. So what you get is you get log base 2 of x equals y times 1, which is y, so that's what your inverse is. So we would conclude that f inverse of x is log base 2 of x. Okay, now it comes in handy to just know that, obviously, but if you forget, that's how you figure it out. Okay, all right, so that would be the idea. So like if you had 3 to the x, what's its inverse? Like that, right? Okay, right? Okay, is there any questions on that? Do I need to clarify anything on that? Okay, all right, it's all important stuff to know. We're going to do, I'm going to go ahead and do the Trig review next on 1.4. I had you pick 1.4 up, I think, today, didn't I? And then we'll take a break after we do the Trig review. Then we'll come back and we'll start into the calculus here today. All right, so let me go ahead and pull this up. Okay, so let me run through here and let me see if this applet on here will load up. If you're not familiar with the website GeoGebra, it's a very, very good website because what they have done is they put together what are called applets, and they are really good visual tools to help students see basic concepts. Okay, I use applets a lot of times in this class when I'm teaching stuff. So one thing, of course, the big thing that you learned in trigonometry, probably the biggest, most important thing, is the unit circle, because all of trigonometry is kind of embedded in that. So this is a kind of an example of showing you how the unit circle goes, and you can kind of drag this point around right here. Just watch this and let's see what we remember. So the first thing is a unit circle. What does a unit circle mean? It means the radius is what? It means it's 1, okay? So if you have a unit circle, you have an infinite number of points on that circle. As I drag this around, like that's the point 1, 0. And if I drag it around, now I've got like a point 0.73, 0.68, and so forth like that. And you're forming a kind of a triangle as you go through that like that. Okay, so what is the cosine on a unit circle? What's its meaning? It's x. What's the sine? Y. Okay, that's the big thing that you want to remember. I can't imagine any trig person getting out of trig and not remembering that, of all things. Okay, so if you look at this particular point right here, you're really at 0 radians. Okay, well, the cosine of 0, or you can look at degrees also, would be 1, the sine would be 0, right? Okay, and if I scroll through this a little bit here, okay, now I'm at a totally different angle. Now this applet's telling you it's 47 degrees, okay? Or I could even, if I'm real careful, I might be able to get to 45, but I don't think I've got a steady enough hand for that. You guys know what the point on the unit circle is at 45, just out of my curiosity? Square root of 2 over 2, square root of 2 over 2, okay? All right. Well, anyway, the cosine would be the x value, 0.71. The sine would be 0.7 and so forth like that. And then when you get up to here, like if you get to 90 degrees, like that, okay, the cosine is 0, the sine is 1, and so forth like that. Okay, that's what a unit circle is. And then you start getting into negative values. The other thing you learned about trig is, like in quadrant 2, the cosine's negative. That's because x is negative in quadrant 2. Okay, you learn the sine's positive, and so forth. You get down to quadrant 3, notice that the cosine is the x value and the sine's the y value. They're both negative and so forth like that. Okay, so that's what the unit circle is, and it gives you a ratio between x and y, and that's what a sine and cosine are. Okay, that's what the definition is. So the unit circle, of course, a couple of things that you want to make sure that you refresh your memory on is in the unit circle, these are your basic trig definitions in terms of x, y, and r. Okay, so you want to remember that and just review that from time to time. And then here's the unit circle. Okay, one of the reasons in trig that teachers are really big about not giving unit circles and having you memorize, because in calculus, and it happens like in my Calc II class, just here and there, we have to just in our head know something on the unit circle. Now we don't draw the unit circle over and over again. It's just the problem point pops up. What is the sine of pi over 3? You want to quickly figure it out. You don't want to go fumbling for your calculator. Okay, you want to figure it out. So the key thing is how this is the unit circle. If anybody needs to review that, I have a video I can put on D2L that shows you how to create that. Now, a lot of you were my trig students, but if you hadn't had trig in a long time and don't know this, it's actually very easy to memorize. So I'm going to post that for anybody that needs that. Okay, so here's basically what we do on your trig here is these are the radian measures, and then these are the points on the unit circle. That's what we just spent a lot of time in trig. So cosine of pi over 6, how do you find that? You look at pi over 6, and what do you look at? Look at x, okay? So the cosine of pi over 6 is going to be square root of 3 over 2, like that. Okay, that's what that is, okay? All right, here's another way to look at this. Unit circle is what you're going to use most often, but pi over 6 is 30 degrees. Okay, so what you get is a 30-60 right triangle. I find a lot of times students remember the unit circle but don't remember their triangles. You guys remember how the sides go on a 30-60 right triangle? 1, 2, square root of 3. Okay.
Square root of 3.
So it goes, 1 goes there because it's small. 2 goes there because it's bigger than 1 in square root of 3, and then that goes there. Okay. So another way to look at this problem is the cosine of 30 degrees is the adjacent over the hypotenuse. Okay, so the adjacent is square root of 3, and then the hypotenuse is 2. That's the second way to look at it, okay? So if you don't like the unit circle, because the thing is, you just have to be able to do things like this constantly in calculus. So either you work with triangles or the unit circle, it's your call. I don't care. Just know it, okay, without a calculator. Okay, how do you find the sine of pi over 4 on a unit circle? Look at the y value, okay? And by the way, that one's the one that shows up all the time, so you may already know 45 degrees, cosine and sine are square root of 2 over 2, automatically, okay? Okay, now we got negative pi. How do you draw a negative angle? Clockwise, okay? Start here and go clockwise. Pi is 180 degrees. That's a fundamental thing that you're never allowed to forget as a math student. That's the relation between radians and degrees, okay? So if it's a cosecant, well, there's a couple of ways to look at it. Which trig function is the cosecant, the reciprocal of? I told you what it was, okay? So this is really 1 over sine of negative pi. That's, one of the basic identities. And then the sine of negative pi would be the y value. So what do you conclude?
It's undefined.
It's undefined, right. Okay, so that's how you go through and figure that out, is you want to remember the cosecant's reciprocal of sine, secant's reciprocal of cosine, cotangent's reciprocal of tangent, and so forth like that. Okay, how's that look to everybody? That's fundamental stuff. This is the stuff you're going to use in trig all the time, okay? All right. Okay, let's see, 5 pi over 6, let's do that. Now, how do you figure out a tangent on a unit circle? It's not as easy as the sine and cosine. What do? You do y over x, good. Okay, so you got to remember that the tangent's y over x. So if you find 5 pi over 6, which is 150, I'm really looking at, this thing right there, then y would be a half, and x would be, and I got the wrong sign there, that's 1/2 over negative square root of 3 over 2, like that, okay? So when you're doing that, if you have a half over negative square root of 3 over 2, well, you can divide those 2's out, because when you're dividing a fraction, you're multiplying by the reciprocal. You would have a negative answer, okay? And then that's okay, okay? There's no law of the universe, by the way, that says you have to rationalize denominators. The reason we teach that in trig is because we want, it's useful in calculus to know how to rationalize, because it pops up a lot. So, but you don't have to. I'm going to go ahead and rationalize it, and that's another thing you want to remember how to do. So you'd have negative square root of 3 over square root of 9, so that's root 3 over 3. That's another thing that hopefully in trig you got down to a science, okay? Okay, any questions about anything with that? Okay. Okay, let's do a equation here. You're going to have to do trig equations, and when we get to that point, I'll have to review that, because I always do when I do calculus, but just a rough review here. Let's solve an equation. Okay, and the first thing on this is I want you to solve the equation from 0 to 2 pi. That means I want radian answers, 1 lap around the circle, right? Okay, well, what if I gave you this problem instead? X squared equals 1/4. How do you solve that? Square root both sides, right? You do the same thing on this. So if you did that, you would have x. Anytime you square root both sides, you got to have plus or minus. Students forget that a lot. Then that would be a half, right? That's how you do that problem. This problem you do exactly the same way. You're going to take the square root of both sides. So you're going to have sine theta. Okay, now that's going to be plus or minus 1/2, like that then. Okay, don't forget the plus or minus or you won't get all the answers. Okay, well, if we go through and I'm going to just go to my previous page on the unit circle and show you a couple of things on here. So if you were to go back and look at the unit circle, really all we got to do to solve this equation is find every place on the unit circle where the sine's a half. So what do you look at? You look where y is a half, right? Because the sine is the y value. So there's one answer, pi over 6. Here's another answer, 5 pi over 6. Okay, another answer, we can also have negative 1/2, so that would be 7 pi over 6. And then we would also have 11 pi over 6 right there. So those are your answers. You have pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 like that. Okay, you guys remember that? Okay. If it was a cosine, then what would you look at? Then the x value, exactly. Okay. So what you would get for your answer then, you just write your answer like pi over 6, what was it, 5 pi over 6, 7 pi over 6, 11 pi over 6 like that. Okay, that's the idea. Okay. Okay, does that look familiar and okay? Okay, now we're going to solve quite a few trig equations. That's one of the reasons why you learn it in trig, is because you'll see it in calculus and higher math, and it just shows up from time to time. The other kind of thing I want to do here, and I'm not going to do much with this, but I think it's helpful. We're going to deal with the inverse trig functions in calculus, and you do that quite a bit in Calc 1, Calc 2, Calc 3. From time to time you work with inverse trig functions. One of the things that's kind of helpful is just you're going to have to remind yourself from time to time of these ranges. Okay, so I'm going to just go through just a few things with this. I don't really probably have a lot of time to go through the details like I can do in a trig class, but the idea, and I want to at least kind of get you through this kind of an idea. So, and you might want to write down just a couple of examples. Mainly I'm going to kind of review these three because those are the ones that show up the most often. Okay, so if you had the arc sine of negative square root of 2 over 2. Okay, let's review what that means. Okay, first of all, the meaning of this statement is this. It means that the sine of what angle is negative square root of 2 over 2. Okay, you're doing an inverse, so you're doing everything backwards. So if I give you a sine, an arc sine, that is a y value. That's the y value on the unit circle, right? What are you finding? You're finding the angle that provides a sine of negative square root of 2 over 2. Okay, everybody got that? Now, I'm going to refer to this unit circle on the previous page. Now, this is what you got to be careful about. This is what students mess up on the most often. So, if you try to find on the unit circle where the sine takes on the value of negative square root of 2 over 2, there's two places, okay? But there's only one answer to an inverse sine. There's only one answer. It's a function, so you're expecting to get one answer. And it's not going to be this answer. That's wrong. It's not that. And it's not going to be that answer. That's wrong too, okay? You have to pay attention to this range. So your answer to this problem has to be between negative pi over 2 and pi over 2. Now what that means to you as a student is 0 to pi over 2 is quadrant 1, right? 0 to negative pi over 2 is quadrant 4. So what you have to give me is the angle that is clockwise from there to there. What is that angle? It's a negative angle. What is it? Negative 45, good, or negative pi over 4. So the answer to that problem is theta is equal to negative pi over 4. Okay? Those are things that are so easy to forget that an arc sine is defined from negative pi over 2 to pi over 2. So your answer has to be within that range there. Okay? Now, I want to show you something on your calculator. I'm going to put my calculator back in degree mode. And by the way, your calculator is programmed to pay attention to those ranges. You need to program your brain to do the same. Okay, so if I do the same problem I did, I would go second sine to get inverse sine to come out. And then if I put in like negative square root of 2, I'd have to put this in kind of carefully like this. Okay, the calculator is going to give that answer in degrees. And see, notice it gets a negative 45, and it only gives one answer. Your calculator is not ever going to give you more than one answer on the inverse trig function, because you can't. There isn't more than one answer. There's one answer. Okay, so that's the idea. Your calculator can bail you out of situations, but you don't want to be totally reliant on it. Okay, well, let's just do one more, and just for the reminding thing here. So let's say we were doing arc cosine of, let's say, negative square root of 3 over 2. Okay, like that. So what that means is, it means the cosine of what angle theta is negative square root of 3 over 2. I think it's important that you can always rewrite that arc cosine into that expression. Okay? Now, on a cosine, you're looking at the x value, right? So what I'm doing is I'm giving you the x value on the unit circle, you're providing the angle, but your answer must be between 0 and pi. If it's outside of 0 and pi, you're wrong. Okay? So I'm going to do the unit circle on the previous page. And find for me where x is negative square root of 3 over 2 and tell me the radian answer. 5 pi over 6. Good. Okay, that's it. That's in range. That's from 0 to pi, so that's a good answer. Not here. Okay, that doesn't count. Okay, it's only one answer. That's out of range. Okay? How's that look? That's one of the things that students do not remember very well in trigonometry when they teach calculus. Okay, the graphs, I'm not going to really go over the graphs of the trig functions, of the inverse trig functions too much. I just wanted to have that for you. We'll deal with that kind of when we get to it. And then the last thing that I wanted to have you guys do real quick is just do 8, 9, and 10 yourself. Just do that real quick. Take a couple minutes to do that. You can refer to my unit circle. And remember, when you have an inverse sine, your range is, you can only give me answers from negative pi over 2 to pi over 2. And when you have an inverse cosine, your answer is 0 to pi. So make sure that the answer you give me is within that range. And you're just looking backwards on a unit circle. And you can just write the answer if you want to. I'm going to write it this way. It's good to write it this way, but you don't have to. The point is that you can interpret the unit circle correctly when you do that then. Okay? Okay, can you tell me what the answer to number 8 is? Radians. Give me radians. Okay, so what is it? Pi over 3. Okay, that's good. Okay. Okay, here's the one that's the one students mess up on all the time. Okay, can you tell me what the answer to this one is? I think I already did that. So I hope you can do it. That's the same problem I did a minute ago. Okay, so that was this. But why do you not give me 7 pi over 4?
Because of the range.
It's out of range. Okay, you give me negative 45 or negative pi over 4 because it fits in that range. That's what you got to be careful about. Okay, can you tell me what the inverse cosine of 0 is? Okay, what'd you say? Pi over 2, okay. Okay, there you go. That's where x is 0. Pi over 2 is in range. See, that's in that range. So the answer would be pi over 2 like that. Okay, that's it. Okay, so those are going to be some things from trig that you'll do from time to time. You'll do unit circle a lot. You'll solve trig equations quite a bit here and there. And you'll deal with inverses here and there too, okay? All right, so not everything. And you'll also deal with identities from time to time. Identities get real big in Calc II when you start doing what we call integrals and you have to start working with expressions. Okay, well, let's take our well-deserved break here. Let's take like 15 minutes. Why don't you come back at 9:55, and then we'll start this chapter 2. And that's really where we start developing some of the calculus ideas, okay?
Oh, yeah.